Huh, what's going on? In Algebra 1 class. The reason why I'm talking like this is because I'm actually talking to this camera, but then that camera's the one that's recording, and there's a lag. So it sounds like a kung fu movie. Huh, hoo-ha, psh, psh. Got it? Welcome to Algebra 1 class. We're going to get started. How you guys doing today? That good, huh? Awesome. No one answers. Natasha, you can turn, you know what, Natasha, let's make this interactive. Can you hear me? Are you using your Chromebook to log in? Did they give the new students Chromebooks? You got a Chromebook? Yeah. All right. Turn on your microphone and why don't you talk back with us? That way you're actually here. It almost feels like we're all here. Almost. Besides the fact there's only one person online, there's a whole bunch of people here. And that's not even my whole class. I've got like a whole bunch of students. You know what, you guys? I know I'm preaching to the choir, but I'm going to send out an email and say, you guys, there's a problem here. We're not attending class. And that kind of is disappointing. Anyway, let's get started with some warm-up stuff. Let's do this one. I'm going to go over to page I don't know, but it's activity 6.2. I'll show you which one I got. It's got to be this one over here. How do I scroll? How do I zoom? All right. Let's start off with some warm-up stuff. Let's talk about it. Okay, you guys ready? What we're going to do is we're going to be looking today at graphs. Now, in science class, I believe you guys are covering energy. You guys are going to be covering like the graphs of energy. So this stuff is really important to learn how to read a graph. So all we're going to do today is cover graphs, 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 and more graphs. And I think this is pretty intuitive stuff. Now, I wish that I had something that worked. One second. Let me grab something. I have this thing. I've never actually tried it. It's a motion detector. Okay. And what it does is it's basically a sonar device. I actually built one of these in college. It shoots out a. Think about it like this. This would be like the radar gun that the cops use, right? It shoots out a signal, goes beep, and then it waits for that signal to bounce off something. Justice's forehead, and then comes back and goes beep, right? And Justice is moving towards me. It takes less time, okay? So what this thing tells you is it calculates out how far that thing is based off how long it took. Is that too crazy for you, or can you guys imagine this thing? Okay, now, let's pretend that this thing worked, and I wish it did. It would be really cool if I had the class that did, and I'm ordering a new one so it will work. Let's pretend this thing works, and I put it right here, okay? So it's facing up, so it goes beep, and then it comes back down, and it's measuring out how long the thing took, okay? And I take a person, they're a tiny person, about that small, and they jump off this cliff, got it? And so it's going to go beep, and you go, signal, 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 and it's going to go faster and faster and faster. That means they're getting closer and closer and closer, right? And so we're going to make a graph off of that, right? But I'm not a completely crazy person, completely. So I attach a little bungee cord to that person right there. And over here is where h equals 0. Does that make sense? This is where the height is equal to 0. If you are standing on top of this sensor, your height is 0, okay? And this is like 50 feet or something like that. So you jump off, and it goes like that. So I have a question for you. What will the graph look like? Will it look like this? Will it look like this? Here's the time, and here's the height. Will the graph for that look like this? It's going to go, for the height, or the distance, is going to get further and further away as the time goes on. Yes or no? Yes? Natasha, I'm looking at your computer screen, so, or I'm not looking at your computer screen, that's a little weird, but I'm looking at your chat, so you can chat back with me unless you want to turn on the microphone. What are you guys' thoughts? Come on. Come out here. If you don't know, say, I don't know. I don't know. You know what? I'll tell you what. It's a yes or no answer. And all I want to do is I won't even look. How's that? Natasha says it would be getting closer. I tend to agree with that. Why don't I do this? I'm gonna go like this. Yes or no, and I want you guys to raise your hand for if you say yes, raise your hand. If you say no, don't raise your hand. Just tell me how many yeses there are, and also count Natasha's answer. Is this the correct graph for this situation? Go. You only got a few seconds. I mean, it doesn't take long to raise your hand. Okay, put your hands down. All right. How many? One. Because that one person is wrong. Because it's actually no. Don't look at the person. That's why I close my eyes. No, it's not. It's not. You're absolutely right, Natasha. It's getting further away. I mean, not further. This is getting further away, right? This person's getting closer to the thing. All right. Right. Okay. So, would the graph look like this? This is getting closer.
Yeah.
I'll give you another chance. Ready? Vote. Yes, raise your hand. No, keep your hand down. Just tell me how many yeses there are. Put your hands down. All right, how many?
6.
6 yeses. Natasha, sorry. You didn't answer in time, so actually we have a record of what you answered, so, closing my eyes doesn't work for you. Throw it up there. Do you think that this is what the graph's going to look like? It's getting closer to the thing. This person's going, and it's getting closer. Is that what it's going to look like? I'm waiting on Natasha. Yes or no? Good answer. She didn't answer yet. All right. Well, maybe she can't hear me. Natasha, can you hear my voice? Can you hear my voice? I'm not sure. I don't think free falling would be constant. Yes, I agree with you. All of you are wrong. Natasha is correct. Sorry, that's just the way it is. I mean, really, people don't fall like this. They don't fall at this constant, nice, floaty rate. They get faster and faster and faster. As you fall, you get faster and faster and faster. That's what acceleration is called. You are learning that in science class, right? So this would be a constant fall, right? But you don't fall like that. When you jump out a window, you get faster and faster and faster and faster. You won't get faster and faster infinitely because eventually you'll be able to go faster than the speed of light if you jump off a cliff high enough, right? So there is some kind of balance off of that, and that balance is called air resistance. But if I were to drop something, air resistance didn't have enough time for that thing to, that thing is going to accelerate. I love your answer. Would you guys actually like to see something that falls at a constant acceleration? And this is just a side note. This is because I'm a physics teacher, and I know physics really well, and I don't think hopefully this worked. It's all crumpled up, but this is a coffee filter, and if you ever watch a coffee filter fall, it's really crazy. It's because the air resistance, the way the coffee filter is shaped, it will fall, hopefully it will fall nicely. Kind of. It's all opened up. And then the second thing is, because the coffee filter is so light in the way it's shaped, the air resistance acts on it immediately. So this thing does actually fall like this. Weird, huh? I'm literally watching a coffee filter fall in class today. And it is weird. I mean, if you look at it, watch. This is what that kind of motion looks like, which is very unnatural. It didn't speed up because it reached its terminal velocity immediately. Okay? But that's just for coffee filters. Everything else falls and it speeds up. And it takes some time to reach its terminal velocity, so we rarely see the terminal velocity reached like that quickly. All right. So it's not going to look like that. I agree with Natasha. it's going to be more like this. That shape, do you know what that shape is? It's a parabola, which is why we learned parabolas in the first place. So is this the graph? Huh? Yes. Yes, 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 yes. Natasha? No, but actually, she takes time to think. It's fine, but I'm putting you guys on the spot. The answer is no. You guys are wrong again. I attached a bungee cord to her. If she just jumped without the bungee cord, then yes, maybe that might be a good graph. I agree with you. But I attached a bungee cord to her so that she wouldn't die. What kind of morbid, sick people are you? All right, fine. Here's the other option. So, Justice, I think you're onto the right thing. You're saying it will go kind of like this, right? Those looks like a bunch of parabolas. Just going to go, oh, woo, 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 right? Is this the graph? Yes, 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 yes. Karang! This is h equals 0. Do you realize what this graph is saying? She's going to jump off the cliff, smack, then go through the ground, negative, and then go back up, and then smack. Even sicker. You guys are just crazy. You guys must like punching babies in your spare time. Crazy people are you? All right. Here's the last one. Is that going to be it? Obviously, it is going to be it because it's the last one, right? But what I'm saying here is, I mean, if you think about it, like, all right, this person jumps off, right? The bungee spring is going to start acting. Luckily, this person isn't going to smack on the floor, and it's going to come back up. And is this person going to come back up to the same exact height that that person came? No, it's going to be a little bit less. And then, well, they're not going to go down as far if they didn't come up as high, and then they're going to go. And eventually, they're just going to go, and so they're hanging upside down like this, belly all showing and all that kind of stuff. Does that make sense?
Yeah. Yeah.
By the way, here's a quick little tie-in. Why don't they come up as high?
Because they lose energy when they're coming up.
Because it's a loss of energy. That's exactly it. When they're up here, they have a lot of potential energy. Have you guys learned energy yet? In science class? Well, when they're up here, they have a lot of potential energy. And then when they're down here, they have a lot of what we call potential spring energy, because the bungee is stretched. And then they come back up here, and that transfers into potential energy. But the reason why it doesn't transfer into the exact same amount of potential energy is because of loss of energy due to friction. The friction in the springy thing, the friction in the air flow. So there's energy lost from there. So all the energy that goes in must come out of the system, even though that doesn't look like it. It's because I haven't graphed the energy that was lost in the system, from all that kind of stuff. This is a little bit of a side, because I'm trying to tie that back into your science course that you guys are going to be taking here in about an hour. Cool? All right. Let's see. We got to get through these things faster. A bicycle climbs up a hill at a steady pace. At 10 miles per hour, she glides down the other side. What does that graph look like? Okay, this is graphing the speed. Got it. So, we have, here's the hill, glides down the other side. Here's the bicycle person. I don't know how to draw a bicycle. Looks kind of like a motorcycle, I guess. Whatever. She goes up the hill at a steady pace, and she glides down the other side. Okay? What will the graph look like? Keep in mind that this is the speed, so I'm going to call it v, which actually stands for velocity, which is a little bit different from speed. close enough. This is the time. So look at those 5 graphs, 4 graphs, whatever. Is it the first, second, third, or fourth? What's your thoughts? The first one. That's what Justice says. All right? You know what I'm going to do is I'm going to 1, 2, 3, or 4. I got 1 vote for the first one. Anyone? You can vote. I won't even keep in mind who's wrong. Because you guys get it wrong a lot. What do you guys think? 1? What about you?
I kind of think it's 4.
All right, so we got here and here. Okay? Jordan, take a guess. You're going to go with 1? All right, follow the bandwagon. What about you? O'Connor, right? All right, number 1. Okay? All right. I think the 4th. Natasha says 4. All right. Apparently it's not the second one. Apparently it's not the third one. This is wrong. You guys went with the graph of what the picture looked like, right?
No. It says it speeds up as she goes. Oh.
Right. But
oh, my bad.
But we told you that while she was going up the hill, her velocity, her speed was constant, right? So we're looking for a horizontal line there. Got it? Because we're talking about speed here, and the speed didn't change. It's just going constantly across, right? If she was going 10 miles per hour, is that what it says, 10 miles per hour?
Yeah.
Yeah, if she was going 10 miles per hour, then this would be 10 miles per hour here, and over here it would still be 10 miles per hour. I don't know how she kept that up, man. She must be just like, I'm going to go up this hill constantly, not getting tired. I would get tired. I'd probably go down like this. Actually, Miss Dolly would probably just go like this and then die. But, all right, so she's got a 10 mile, so it's got to be the 3rd or the 4th. Now, as she goes down the hill, does she speed up or does she slow down?
Speeds up.
She speeds up, so speed goes up. It doesn't look anything like the picture, but I mean, remember, we're graphing the velocity here. We're not graphing the height here. If we were graphing the height as a function of time, the graph would look different. It'd probably look a lot closer to what this thing looks like. You know what I mean? Does that make sense to you? Cool? Yeah? We like it? Awesome. Good job, Natasha. I just did 2 problems straight out of your homework. Let's do another. What? There's only 1 more problem from your homework? Oh no, there's 2 more. All right. So that means you only have to do 1 thing for homework in this activity? I almost feel like I'm cheating. All right, which one do you want? I'm going to ask you this one. Do you want 4 or 5? Natasha, you get to choose. Do you want me to do number 4 or 5 for you in your homework? And she's like, what kind of class is this? Yeah. Yeah, what's your question?
Is function 6 replacing the
Function 5?
function 5 homework
Yep.
today?
Mm-hmm. And I'm going to kill the function 5 homework. There is no function 5 homework at all. I mentioned that in class last time, didn't I? Or were you guys in class? Yeah. I mentioned that, right?
Yeah.
Yeah, I just didn't send out the email yet. But function 5 homework, I'm going to give you guys full credit, and you guys don't need to turn in nothing. All right? Because I didn't really like the assignment.
So this is due today.
Oh, no. Function 6 is still due when function 6 is due. I'm not moving up that due date. So is this due like next week? I think it might be due later on. Is it due today or due later on? I didn't check the due dates. Huh? It's due later on? Psh, looks like you guys got a freebie. All right, let's do it. All right. It's undated. Oh. Well, I will make sure to put a date on that. I'm so sorry. Yeah, function 6, I was supposed to, I guess I need to put a date on that. All right, sorry. Natasha says she wants me to do number 5. Wait, number 4. So let's do number 4. That's what she said. 5, and then she put 4. All right. And eater at the zoo is given ants for lunch. He slowly eats 4 ants and takes a break. What kind of lame? Ants aren't very big, dude. How are you gonna eat 4 ants and then take a break? He's like, oh, I'm so tired. There's so much ants to eat. He doesn't even have to chase the ants. He's given 4 ants. And he's given ants for lunch. What a lame anteater. You know who's the anteaters? Is UC Davis, I think. No, one of those University of California ones, and they're the anteaters, and apparently their cheer is like zoop zoop. I swear that's it. I don't even know what that's all about. Anyway, they ate 4 anteaters for lunch. This is why we take so long in class with Mr. Dalton. Keeps telling stories. Repeating this pattern throughout lunch, the graph below depicts the number of ants remaining at the beginning and when the ants are delivered. Okay. So, anteater. To be honest with you, I have no idea what an anteater looks like. I suppose that I might have just drawn an armadillo. Okay? You got a big stack of ants. Okay? Here's ants. Here's time. How does that graph look? 1, 2, 3, or 4. Let's take a guess at that one.
3.
3, 4. 3, 4. Justice. 4. 4. 4. 4. What about you, Natasha? It's 1, 2, 3, 4. Oh, Natasha says 4. What about you, Mario? What about you, Bailey? All right, Mario says 1. We got another 4. All right, let's take a look at it. Oh, I got another 4. All right, yeah. All right, I'll tell you an answer. No, wait. Actually, it's 2. All y'all are wrong. Seriously. Because look. I was just thinking I thought it was 3. But it's 2. 3 would be the scenario where he has the ants, and then he like eats 4 in one bite. And he eats 4 in one bite. And he eats 4 in one bite. Waits a little bit, eats 4 in one bite. Got it? But that's where they didn't say that. They actually said he slowly eats 4. So it goes down 4. And then he waits a little bit. I have no idea why he waits. And he slowly eats another 4. And then he waits a little bit. He slowly eats another 4. And he waits a little bit. He slowly eats another 4. You guys get it?
Yes.
How did you all get that wrong? All right, wait. Okay, let's take a look. What would the graph of number 4? Let's try to think. I'm trying to get into your heads here. You guys all said 4. This is the graph. Can you describe for me what that scenario of that graph looks like? I can think of one off the top of my head. This anteater is God, and he's creating ants, and he slowly creates 4 ants, takes a break, and he slowly creates another 4 ants, and takes a break. See, over here it starts off with 0 ants, and then all of a sudden you have 4 ants more, and 4 ants more, or however high that graph is. I'm not sure, they didn't put units on it. But you guys understand how this is a little bit backwards from the actual scenario that it goes. It's either that, or maybe they're just counting the number of ants, and so they're like, hey, you pooped out 4 ants, right? There's just 4 more ants inside of this thing. It must come from somewhere. He just crawled out of his mouth or something like that. Or a snout. I'm not sure. That's an armadillo. That's not an ant. Do we have, I don't even know if we have an anteater in our zoo. Oh, we do. We do. I remember seeing the anteater. He's always sleeping. Every single time I've gone to the zoo, it's always like in its cave.
Did you ever try knocking on the window?
No. That's not one where you knock on the window. So
it's like a cage.
yeah, no. It's not even a cage. It's kind of like a cave, I guess. Anyway, let's do this one. All right, here we go. Ooh, this one's cool. All right, take out your packets. We're going to do this one. So the point that I'm trying to make here, let's see, match the graph appropriately. All right. The point that I'm trying to make here is that we've talked about functions, okay? Now we've talked about functions. The first time I've ever introduced you a function, I told you about chicken katsu. That was a story, right? And then what I've been talking to you about is we talked about functions as an equation. I like functions as an equation because it's the shortest thing to write. Right? I write down this one line, I mean this whole big story. Okay? Another thing I can do is I can talk about functions as a graph. When I have a graph, you can easily see what's going on. Okay? So now what we've been doing is we've been trying to translate from the graph over to the story to see what exactly is going on. So in this exercise, I only want to do one of them. I think this would be fun. Let's do B. The average of Honolulu Airport. In this exercise, we're going to take the story and we're going to try to match the graph to it. What? This is page warm-up 6.3. It would be, actually, this would be warm. I'm sorry, I'm going to go back one. There we go. I'm going to do one of these for you, and then I'm going to do one of the other ones, and the other one is your homework, so this one's like the warm-up. Actually, you know what, maybe I'll do only the warm-up, and you guys do your own homework. How's about that for a novel concept? All right, ready? Let's do this. Part A. The number of tourists in Hapuna Beach. Is there actually a Hapuna Beach? Does that like actually exist? All right, I don't know. It probably does, right? Throughout one day. The park opens at 8 and closes at 6 p.m. Notable increases seen before lunch and dinner. All right. So, what would that graph look like? The number of visitors would be the first, second, third, or fourth. I know this is a little bit weirder, these graphs. What's your guess? Give me a guess. You don't even have the page in front of you. Here. Take mine. Wow, you're welcome. McConnor, can you go turn on the lights? The lights are right in that corner, right by the door. And you can take off your backpack. Please feel comfortable. It's like you're ready to leave already. All right. Come on, you guys, online. Is it 1, 2, 3, or 4? By the way, how is the sound coming through? Is the audio coming through all right? Can you guys hear me? Is it glitchy? Good? All right. I'm trying something new. I'm actually running this entire class through a Chromebook. Because my Mac keeps crashing. And I'm wondering if the $200 Chromebook can beat out the $2,000 Mac. Weird, huh? Anyway, what's your guess? 1, 2, 3, or 4? Don't worry, I'm not going to put your name above the thing. 2. All right, so we got 1, 2, 3, or 4. I've got a 2. Who else is up there? 2? 2. What's your thoughts?
2.
2 and 2. All right, Makana, Jordan, 2, 2. Sarah? 1. Ooh, switching it up. All right. I think that Sarah could be correct. However, I think that it's a little bit more random than that, so I would say it's 2 as well. But very close, Sarah, because I think that, let me get into your head a little bit. You were saying that the spikes happen at lunch and breakfast, or what is it? I don't have the thing in front of me. He stole my paper. Was this? The spikes happen where? Oh, before lunch and dinner. So you know what? To be honest with you, I can't even tell.
I think it's 1.
I think it could be 1 or 2. I agree with you. It could be 1 or 2. It's definitely not 4. So
Because it should be like before lunch.
yeah. So let's read the next one. Let's see if the next one like actually matches the graph better. All right, let's see. Why don't you read it out to me? Because I can't see it.
The The average for Honolulu Airport shows increases of flights for work rush hours of 7 a.m. and 5 p.m. and greater lulls at 2 p.m. and after 8 p.m. Number of flights versus time of day.
All right, I would say that that's one, definitely. And here's my thoughts behind this. All right, now to be honest with you, if you want to answer that as if you want to say that the Hapuna Beach one is number one as well, I wouldn't really be able to tell you to fault you for that. You know, I would actually probably give you points for that, which is why I grade those things as opposed to having the computer grade those things for you. Because I would think that, okay, I see where your thoughts are. I can see what you're thinking. But I would say for the airport one, that one's definitely one. It's definitely not two. Would you like to know why? This is my reasoning. Is because for number two, that's talking about the number of people going to the beach. That can fluctuate really quickly because you can just, how hard is it to have a different person go to the beach? Just, there I'm at the beach. There's somebody else. You know, so that graph will fluctuate. You know? So that's what that graph looks like to me. It jumps up all over the place. With an airport, I would think that like those planes don't just like, hey, we need more flights. All right, add in a plane. Go for it. Throw it in. You know, I got one in my pocket. Here. There you go, plane. Right? No, it's probably very scheduled, regular things. The first one looks a little bit more scheduled and regular to me. And the second one looks a little bit more random to me. Does that make sense to you? So I would agree. I think that for part A, that was number one. That was graph one. And for part B, that's graph number... No, I'm sorry. I got that switched. For part A, the Hapuna Beach one, that was graph number 2. For part B, the Honolulu Airport one, that was graph number 1. You guys agree? Or it could be number 3. It's tough to tell with these things. Can you read the next one for me? See?
NASCAR racers travel around a track and stop an average of 6 times per 1,000 kilometer race. The race lasts about 4 hours and they stop at the same place each time on the track. Distance from race finish line versus time.
It's definitely 4.
Yeah.
That's definitely 4 because it's very consistent. You know what I mean? I think I was watching Turbo the other day, and they're like, "I love NASCAR. Left turn, left turn. Oh, what do I do now? Left turn, left turn, left turn." Because they're just going around in circles, and then I tease that, and then somebody's gonna be like, "Dude, don't diss NASCAR." Right? And I'm like, I don't know. I mean, I think it's a sport. Left turn, left turn. All right. Anyway, I definitely agree that would be number 4. All right. Coco, why don't you read the D for me?
Surfers paddle out to the break and crash an average of 5 waves within an hour. Distance from shoreline versus time.
Five waves in an hour? Wait, what? Read it again?
Surfers paddle out to the break and catch an average of 5 waves within an hour.
Huh. You know, to be honest with you, I think that's number 2. I really do think it's number 2. Because that's the only one that has the 5 waves, or the 5 spikes. It actually only has 4 spikes. But I mean, they say an average, right? So it doesn't have to be exactly 4. Remember, think about this. Okay, come on up here. Okay, you're on the beach. There's a little like hanging out on the beach. I'm a surfer dude, and you're like, yeah, watch me surf. So what you're doing is you're measuring. By the way, Kay's over here with a motion detector. It's actually measuring how far I am, and you're measuring how far I am while I'm on the beach. Do you surf?
Yeah.
All right. So, yeah, you look like a surfer dude. Come on up here. All right. So I'm just trying to think of this scenario here, and so you're going to paddle out, right? When you paddle out, is it just constant like boom, and you just go? Right. No. you're kind of going like here and then back a little bit and here and back a little bit and here and back a little bit and here. Why do you go back a little bit? Because the water, right? It kind of like moves you back and forth, right? So your graph is probably going to measure all kinds of crazy stuff, right? And then you catch a wave. Sweet! And then you come back and you're like, all right, cool. Then you come back in. You go back a little bit, and back a little bit, and back a little bit, and then you come in and catch another wave. Go! And you come back over here. And then that's your second wave, and a third wave, and now catch a crow. All right, wait. Okay, wait. I'm looking at this graph over here. Oh, hey, catch a wave. There we go. And then you go back a little bit and get a little bit washed out, and then you go back to your the beach, and you're like, wasn't I an awesome surfer? I think that that's number 2. That's what it looks like to me. You guys agree? That means, Sarah, I would actually might even agree with you now and say that the Hapuna Beach one was either number 3 or number 1. It might be number 1. I'm thinking that it starts off slower because it starts off at, what is it? That almost looks like it starts off at 0 or close to 0 because I'm thinking that before they opened up the beach, there's not a whole lot of people on the beach. They said that the beach is open only at certain times, right? So why didn't it start off at 0? Well, I guess maybe there's people sleeping on the beach or something, you know? Those are the campers or non-campers. We get it?
So 1 is
So 1 is A. Yeah, I think so. We cool? Can you guys do your homework part for you? Can you guys do your homework part? All right. All right. Cool. Time of Scott's finished. 10:30, right? So we got an hour. Well, that's fine because I think I actually just finished chapter 6. Right? Check the next page. Am I done?
now 6.3.
Oh,
yeah.
Yeah, because the next part is just your homework, right? All right. I'm not going to do your homework on that part. I'm just going to do the warm-up for you. But I feel like you've got it. I feel like you understand how to translate from a graph to a story. Cool? What's coming up in 7? Ooh, it's a skateboard ride. Graphing in context. Ooh. Let's do this. Because it's more graphing. I like graph. I mean, it's not even that bad. Right? So do you guys have 7 on you? I happened to print up the entire packet for the rest of the quarter. For those of you who didn't, do you actually have the packet? Did you print up everything? You did? You don't have it with you? Alright. Here. Give me my chapter 6 stuff back. Come on, you expect me to get up there? I've been standing up all this time. Come on up here. Alright, here we go. I'm going to give you guys one. I only have 3 of them right now. I can go right now and go grab another one. I'm going to pull it up on the computer as well. So those of you who are sitting on your butts at home, that's fine too. So I expect you guys to finish chapter 6 because I finished like more than half of it for you. Got it? Alright. Team Coco, you guys get one. And Sarah, you get to share. You guys just share. Share the packet with each other. Let's take a look at number 7. Give me a second. I'm going to upload this thing to the computer right now. Why don't we take like a couple minute break? Breaks. Now, for those of you who are brand new, so we're actually going to spend the next like 3 weeks on graphs. How are graphs? Are they hard? Well, to be honest with you, actually, that one thing where we were trying to figure out the Hapuna Beach one, that was actually kind of tough. But I think it makes sense. And I particularly like the surfing kind of thing where I had to push you around. Not to say I like pushing around, but I kind of did. It's fun. All right, give me a second. I'm going to upload this thing to my course. We'll see. By the way, who did I got online? I got Bailey, Mario, Natasha.
Are you using big blue button?
I have a big blue button in it.
Mine's not working.
Mine's is actually working good on the Chromebook.
Mine is like an epic fail. No audio, no webcam, no screen sharing, anything else.
Get a Chromebook.
Right.
How lame is that, right? The $200 machine, right? All right, anyway, let's do this one. I think she just gave me the. Didn't she? She kind of did, yeah. It's kind of that. All right, let's see. Yeah, the Chromebooks are all right. They're not that bad. All right, let's do chapter 7. Got it? So I'm on chapter 7 warm-up. I'm going to do some of the warm-ups for you guys, with you guys. Let's do it. Where'd you put your skateboard?
It's in.
No, you left that one to use it as an
You want me to
example.
go get it? I want it actually. I need it here.
Walk very quickly. I'm not saying to run, because I'm not condoning running, but if you want to get quicker than even walking quickly, I don't mind. I'm just saying.
Yeah.
Officially on the camera, I'm telling you not to run. But hurry. 1 second. We're getting the thing. Why don't we read the problem and then we'll have him come in here and he'll act it out and he'll just be like, what's going on? All right, let's try to figure it out. All right. Sierra goes for a ride on her skateboard. Let's make it. Jordan goes for a ride on a skateboard in a straight and level street. He starts from his house and is located at the end of the street and travels up and back. Below is the graph of his distance versus time. What is Sierra's doing from B to C? Explain. During the travel. Okay, all right, I got it. So here's what we're gonna do. I'm not gonna say anything. I want 2 volunteers. I'm gonna use you. Thank you for volunteering. Next one. Actually, I only need you. All right.
Oh, that's kind of.
So what we're gonna do is I'm gonna back up the computer. I'm gonna have you push him according to this graph. But don't worry. All you gotta do is stand up here and look pretty. All right? With your muscle shirt on. Just look pretty, all right? And then you do what they tell you to do. Okay, so he's going to stand over here, he's going to stand on a skateboard, and you kind of push him this way, and then, and let's try to emulate this graph. Okay? And you know what? Let's just do it without really saying anything to him. I'm not even going to tell him, stand here, this is what's going to happen, blah, blah, blah. I'm just going to be like, he's going to be like, what's going on? Okay? Let me just move this. Don't push him over. All right? I can do without any lawsuits. Let's graph this. So, this thing looks like. All right. Here's the graph. You guys ready?
One of the ladies said, "Don't fall in drinking it."
All right. I'm going to back up the camera a little bit. Turn the thing around so I can see like this. All right. Go for it. Help him out.
Get him first.
Hey, wait, by the way, he's on a skateboard. Just make sure you go. Hey, graph for me what A and B looks like. A to B looks like. Come on, you guys, you gotta tell him what to do. Remember, he's Vanna White. He's looking pretty here. And by the way, may I say you're doing a very good job. What is that? Okay. Just keep going? Dude, we don't have any more room. You guys got to help him out here. That's what the graph looks like?
No.
All right, reset, come on. Okay. All right, what's going on from A to B? Those of you online, you can answer, please. All right, I'll tell you what. Do you think you understand this thing? Can you just... sorry, Vanna White, you're going to need to have a brain here because the rest of the class isn't telling you what to do. They're all scared. Do you think you might be able to graph...
So it's time by distance?
Yeah, this is distance on... the vertical axis is distance, the horizontal axis is time.
So this is time and this is distance. So time
Yes,
and
this
distance.
is time, that's distance.
Time and distance.
Yes.
Okay.
Take go.
Time and distance.
All right. He's thinking. Take go.
Okay.
Okay, got
So
it.
this is what's gonna go down. He's going straight, right? And it's gonna take a little bit of time. And he's gonna stop. And then he comes back a little bit, right? He stops. And he goes a little bit forward some more.
I like it.
Then he
I
stops.
like it. Yeah.
And then he comes all the way back to where he first started.
Very good. Everyone give him a round of applause. Awesome. That was awesome. Good. So what did he do between B and C?
Stop.
He stopped. Why did you stop? Why did you stop? I'm just wondering, were you picking your nose? Were you like you saw a penny? You're shining.
I was live or trick.
You were working on a trick.
Yeah.
All right, fine. All right. Okay. And then what's the next question? During which times did Sierra travel away from, which times did Jordan travel away from his house? At what time? Between what time and what time? A and B. I agree. There's another time. E and F. You know what I liked that you did? You know what I really liked that you did? You actually made him go faster between E and F than you did in A and B. And I didn't draw the graph very pretty, to be honest with you. If you look closely at this graph, I would say that the graph between A and B, that line, is a little bit more slanted between E and F than it is between A and B. So that means his speed wasn't as fast as the first leg wasn't as fast as the second leg. I like that you did that. I don't know if anyone else caught that. Did you guys catch that? He pushed him a little bit faster on the second time when he went forward. But and that makes perfect sense. And then he brought him back really quickly. So you actually matched the graph very, very well. And between C and D, okay, well, what's the next question? During which time, oh, oops, I just answered the next question. During which time do you think he is going fastest on the skateboard? Online, I want you guys to throw it up there. What time was he going the fastest? E and F, okay? Do you guys agree? That's only one person. Is that Natasha? Thanks, Natasha. Do you everyone agree? To be honest with you,
I think it's G-A.
you know what? Actually, I agree with E and F. It almost looks like it could be G and H, but here, look at the graph. Look at the graph itself on the paper. And if you look at where those tick marks are, we're looking at the slope, right? What is the slope of G to F? It goes up how many and across how many? Go sit right next to her. She has a thing you guys can share. But look at the slope. I don't know why I'm showing you this page because it's right up on your computer screen, but it goes from G to F. How many does it go up? Can you guys see those lines? Did they print out all right? Here, look at the same graph. Come on, you guys. Put your pencil at G, go to A, F. How many times did it go up? It went up 7? 1, 2, 3, 4. I don't see 7. Or no, I'm talking about going from E to F. E to F. It went up how many? If I'm standing at E and I'm going to get to F, how many stairs? How high do I have to climb up first? 5? I don't see that either. 4, exactly. It's 4. You have to go up 4 times. You guys see that? How many times do I have to go across to get to F? What is it? 1. So what is the slope of E to F? 4 over 1, also known as 4. Got it? Now, we're talking about, so Jordan's speed is 4. I don't know, 4 miles per hour, 4 meters per second, 4 something. They don't tell me exactly what they're talking about as far as units go, but it's 4 something, right? What about from G to H? If you want to go to start at G and you want to start at H, how far up do you have to go? Come on, you guys. You guys talk about it with each other. I'm going to ask you the question next. How far up do you have to go? You have to go 7. But wait, you guys should tell me something. Yeah, exactly. You should be like, you don't go up at all. What are you talking about, Mr. Dalday? Right? You go down 7. Okay, fine. But technically, I could say how far up you have to go, and you'd say, well, you go up -7, right? Which really means you go down 7. Okay, so we've got -7 in the numerator. Okay, how far across do you have to go from G to H? We're talking about horizontally here. 2, right? So, from G to H, it's -7 over 2. Write that down. And use your calculator, Sarah. What is 7 over 2? Some of you don't have to use your calculator. Sarah, go for it. Throw it out. I think this might be getting too deep into the question, but I mean, this is how my brain works. I want your brain to work the same way. Let me model it for you. What is it? 7 over 2? Three and a half. All right. So his speed from G to H is -3.5. His speed from E to F is +4. Do you guys see how I kind of went about figuring that out? The slope. So which one is he going faster in? E to F. Now looking at the graph on the board, you can't really tell. Looking at the graph with these little grid lines over here, you know, a much more nicely drawn, accurate thing, that's what it is. But that's what that translates to. The slope of that line is how fast you're moving. Does that make sense? Are we cool? All right, I'll tell you what. Turn the page over. We're going to do one more. I'm going to do some more for you. And then you know what? Yeah, why don't we do as much of this as we can? I know that I'm going kind of quickly, and I know that I'm going a lot, and I haven't even given you guys much of a break. But I haven't pushed you guys too extremely hardcore. What time does your class start?
10:30.
You want me to finish a little early so that they can have a break, so that way you can kind of have them fresh minds as opposed to like drained?
Are you exhausted?
I haven't given them a break. We've been going straight for an hour right now.
It's up to you.
All right, I'll finish at 10:15.
Yeah,
Sound good for you?
10:15.
All right. Is that all right? Can you guys hang in there for another 15 minutes? Or do you want a 5-minute break and I'll just go straight to 10:30? I can do it. All right. All right. Let's do this next one. Let's read it, okay? Makana, why don't you read this for us? Not to say that I can't read. I just want you to read. Yeah, that one. Perfect.
Yoni takes the bus to school and he must walk and or run to the bus stop in order to catch the bus. The bus stop is located about 1 mile from his home on the same street. Assuming FT represents the distance from here to his home at time t, where t equals 0 represents the time he left home. Graph of approximate functions of f versus t for each storyline. Below from the time he leaves his house to the time he boards the bus. Note, you do not need to consider the sequence.
All right, Sarah, I'm going to want you to walk out the first example for us. And it's Sarah walks at a constant rate and arrives 10 minutes before the bus arrives. Okay? Justice, you're my cameraman. Here's the camera. Stand up here. Grab it. There we go. Sarah, you'll be our actress for today. Here's your home. There's the bus stop. I don't want you to take 10 minutes, but I mean, there's your home, there's the bus stop. I'll be the bus. Bus. All right, ready? Sarah walks constant rate. She waits 10 minutes. Hey, you need a ride? Come on. There we go. Come on, Sarah. Got it? What does that graph look like? Sarah doesn't need to graph it because you guys saw the picture. She was the actress. What does the graph look like? A straight diagonal line. Did I just tease you? Or do you actually? Okay, I don't mean to make you feel bad. All right. I realized. Wow, that was a punk move. I'm sorry. I'm going to apologize to you for that. Yes, the straight diagonal line. And then what? And she waits, so it's plateaus off. Cool? When the bus comes, hey, need a ride? All right. Next one. Makana, you are my actress. You ready? Where's the next one? Here, come on up. Why don't you read it for me? Here, there's your home. Here's the bus stop. Number 2.
Keone is late. He runs as
Makana.
fast.
What does this mean, Makana?
Makana
And she.
is late. She runs as fast as she can until she gets tired and then walks the rest of the way, arriving just in time to catch the bus.
Okay, ready? Okay, go. Well, you're going to run as fast as you can and then get tired and walk the rest of the way. That's all. All right, ready? Acting it out. Action. Hey, need a ride? Let's go. You guys got it? All right, graph it for me. Awesome. By the way, great running. All right. What's that graph look like? Which one? Okay, wait. I'm confused. This was the first one. What does that graph look like?
She's going at constantly. She stops, waits, and then she goes in.
Does she wait? Does she? I mean, I know that's how she acted it, but that's not what the story says. She didn't go like.
It changes speed.
Right? That's not what happened. But she's not that out of shape. She just ran as fast as she can, and then from here to here, she got tired. That is kind of out of shape. I mean, that's like eating 4 ants very slowly, but I'm just saying. At least I can run from here. I'm just messing. This is a story, right? We're pretending. This is like a mile long or something like that. All right? Come on, tell me what it's going to look like. That was the first graph. This is the first graph. Does not make it the same person. Let's make it different people. So first Sarah walked, waited 10 minutes, boom. Bus picked her up here. What does Makana's story look like? Is it going to be a straight curvy line? Or is it going to be, there's no such thing as a straight curvy line. Is it going to be a straight diagonal line? Yes or no? Yes. Yes, it will. Say it with confidence.
Yes.
Yes. Awesome. Now, will it be more slanty or less slanty? Say it with confidence.
Less.
Less. Less. You say less?
More?
More. More. You were actually right the first time. You said more.
Oh.
But then you all, got all scared and said it was like, no, I'm so scared, I'm just going to say less. No, it's more. Yes, exactly. Why is it more? Why?
Because she's running.
Because she's running. So she has a greater slope. So it's faster.
The first one. And we're talking about she stops and then she starts walking.
Oh, okay. You thought I was talking about the second scenario. In that case, what does that graph look like? So it looks like this. Now, if she were to really stop, then it would go straight and then go like that. But I don't think she stopped. It doesn't say that in the story. She just ran, got tired, started walking. Right? And actually, to be honest with you, this graph is probably going to be shifted off a little bit. Like this. Because she left a little bit later than the thing. Right? Does that make sense? All right, cool. Next scenario, we'll have Team Coco. Come on up. Who wants to act? Who wants to read?
All acts.
Ooh, we got an actress in the house. Well, you were the beach girl, so. All right, read number. You know what? Let's switch it up. Let's read number 5. Wait, I want to do this one. Hold on. Wait. I like this one. Let's do number 4. I'm going to switch it up. Okay? It's on the next page. You guys got it? Number 4. It's at the top of this page right here. I want to see what. I want to read the scenario because I kind of want to do that. Oh, no. All right. There you go. All right. Go for it. Read it. Read it and act it. I'll be the bus. There's a bus stop.
Alright, this
Okay,
time
ready?
Coco is really late. She runs as fast as she can all the way to the bus stop, but runs slowly and slower as she gets tired. After all, it is a whole mile, but she appears to have missed the bus. She waits and waits about 20 minutes, and then remember it is...
I don't know why they're laughing. I just think it's funny that I'm laughing really that they're laughing. All right, go.
Prince
And also that she
Coco.
ran all this way and waited for the bus, but keep going.
Prince Coco.
Why is it so funny? Okay, go. Compose yourself.
Prince Kalo a holiday. She runs as fast as she can home, exactly the same as on the way to the bus stop. Fast as fast and trying when she approaches her destination just in time to catch the end of the morning cartoon.
Sweet. Just watching cartoons on Prince Cahil Day. All right, cool. I actually wanted a scenario where shit like someone missed the bus and I was just like, hated to ride. Suckers! Okay, but I couldn't find one like that. So this one came up pretty good. All right, let's graph this one. Let's take a look at this graph. Haha, smucks. All right, you guys ready? How does this graph look? It's gonna wait. She ran for the bus, and she slowly slowed down. Is that what it said? It was hard to hear over the. So she ran for the bus, and she slowly slowed down. So she was running. She was booking it like this fast, kind of, right? Let's graph out her whole story. Okay. She ran for the bus. Is that the graph? It's a high slope running. Right? Then she waited 20 minutes. And she ran home. Now, please read the last part where she runs home again. And Coco, why don't you read it? I just want to hear it correctly.
I run as fast as he can. Oh, you know, exactly the same as on the way to the bus stop. Fast in time when I approaches my destination.
Wait, did you say fast as fast?
Yeah.
That's poorly written. I'm sorry.
Just in time to catch the end of the morning cartoons.
All right, so it's similar to the way there. You guys agree? I think this is wrong. This graph is not correct. Why?
Because doesn't she say that
Doesn't it say that she's what?
she's slowing down while she's sprinting?
She's slowing down while she's sprinting, so what would that graph look like? What would that result be? I mean, she's booking it right here, right? Yeah, high velocity. And then she kind of has a slower velocity, right? In fact, do you remember what I taught you guys when I taught you calculus last couple weeks ago? Was that hard, by the way? I was talking about, like, how do you get the slope of a curvy line, right? And I told you about the tangent line, right? So let me show you guys kind of what's going on. I need a ruler. Should have one back here. Do you know where that meter stick is? The one we had, Manic stole it. Do you know where it is?
I know there's.
I just need something straight. Not here, this one. Why do we have a rod inside this class? I have no idea, but we do. Check this out. Over here, the tangent line is a high slope, right? This, I would say, is more of the graph. Because over here, that tangent line, that slope isn't as high as was before. Then over here, that slope, because I'm doing a tangent line, right? Do you guys agree that that's what the tangent line looks like? This tangent line, this thing measures the velocity that she's running at that particular time. That tangent line has a lower slope, so therefore she's not running as fast. Then over here, she just kind of tapers off and dies. Doesn't literally die, she just waits 20 minutes for the bus, thinking that she's late for the bus. Turns out that it was Prince Cahillo Day. She's like, oh, wait, I can still catch. What are you guys watching nowadays?
I watch
Pokemon. I can still watch Pokemon. Let's go.
Tom and Jerry.
What? I wasn't teasing Pokemon. I wasn't. In fact, actually, I'm on episode. Let's see. I've been watching Black and White with my kids. The Pokemon Black and White. And the kids, we're on the Boston City, buddy. I know Pokemon like Daramaku. I think my favorite one is Snivy. She's all stuck up. It's Snivy. But anyway, yeah. So I think the graph looks more like this, right? And then she waits 20 minutes. And then it's more like, wait, this one looks more like this. High velocity down. It actually kind of tapers up like that. Weird, huh? No, wait. Is that? Yes. Because her velocity is high over here. And then over here, I need a less slopey line. So it's actually more horizontal. Does that make sense? So when you actually want to talk about the most accurate graph, like I'm sure that most students are going to draw this, this, and this, and it's wrong. And I'll give you guys like 3 points out of 5 points for that problem or something like that. Because it's not completely correct. I'll still give you some idea, because I think you have the idea. But technically, it goes up and it kind of tapers off because she gets tired, then waits 20 minutes, then goes down at a high angle, and then tapers off to get more horizontal as she gets tired. Does this make sense to you? Could you do that on your own? Not really, but now that I've shown you, at least you know that at least it's in your head. Thank you, cameraman. Are we cool? By the way, how's the audio coming through? Is the voice all right? feel like you're really getting it, by the way. Like you're really kind of, all of you. I appreciate you saying that, like, I'm talking about the velocity and things. I think that you understand that. And that's really good. That's really good for getting this class moving along. But is this making sense to you? Okay? What I want to do is I want to make math tangible to you. I want to make math be like, this is relevant to my life. And I understand how this could work. Okay? Math is not a whole bunch of like fancy formulas that I just pull out of my butt and throw it up on the board and say, memorize this for the rest of your life. If I ever do that, and I'm an Algebra 1 teacher, I'm an Algebra 2 teacher, so I might even have you guys again teaching you Algebra 2. I'm going to teach you some crazy stuff. Don't ever let me pull equations out of my butt and throw it up on the board and say, this is where they come from. I mean, I'll do that. I'll pull equations out. Not from there, but I mean, I'll pull equations out and throw it up on the board and say, memorize this. But what I will always want to do is give you guys a reason for why you should. Show you where it comes from. It's not magic. Math is not magic. I think that's what makes math so hard, is I don't understand where it comes from. Well, I can see how this graph kind of works now. You guys agree? We good? Awesome. Let's keep going. So I'm not doing every single problem for you guys. But let's see what else we got. What happened to my computer? There we go. All right. Yeah, me and my kids watch Pokemon Black and White. And I think after that we're going to go back to watching Pokemon Indigo City. Oh, what is this? Oh, this is really cool. This is a great... Yes, I want to do this. The following graphs Keone's distance from home on various days he's traveling to the bus stop. For the distance of Keone's movements and walking and running at a constant rate, speeding up, slowing down, change directions. Then graph Keone's approximate velocity at the time corresponding to the distance graph. This is a really important concept that I want you guys to try to understand. And for those of you who, I'm going to see if I can get an app working. It's called PHET. This is physics app. But this right here, I haven't even taught my physics students how to do this stuff yet. This translating from graph to graph. But it's really important. And you guys want to know something? This is actually what we do in calculus. This is the beginnings of calculus. So again, we're going back to calculus, and I know that might freak you out, but remember, it wasn't that bad when I showed it to you last time. It's not going to be that bad. You just got to think about it, okay? Let me show you what Keone's graph looks like. I'm going to put two graphs up here. I want to get to this part because this is really important stuff, especially for your science class. You guys use Tracker, right? And it kind of worked halfway. It didn't really work that well. On Tracker, you can really show this. So I wish I could have used Tracker. But anyway, let's do this one. This is the motion that they go through. Okay? Describe for me what that looks like. Describe for me what that scenario is. Can you guys imagine how that, or tell me how I should run? Or you know what, Jordan, get on your skateboard and let's actually push you around. Because I know that you're itching to do that. I see it in your eyes. What's going on, Sophia? No. Here, you ready? Don't break your head. Okay, so here's what's happening. Here, let's straighten you up. Straighten you up. You're going to run into the wall. There we go. All right. So I'll tell you what the scenario is. Jordan is going on a skateboard. And the way he's propelling himself, I'm going to make up the story here. The way he's choosing to propel himself today is with jet propulsion. He doesn't have a jet on him. So he's farting. So he lets one big one rip. The whole time, it's not even like it's a constant. Just going, right? At the beginning, he's going to start off going like fast. He's just going to go and just like shoot off. No? What's going to happen? Tell me. Describe it for me. Do it while I'm... Keep going. Come on, talk.
He starts off slow. He's gonna start going.
He's going to start going?
He's not gonna go as fast, but he's gonna start going.
He's going to start going.
He's gonna start going, and he's gonna start increasing.
And then he gets faster, 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 right? That is actually exactly what the scenario is. He starts going, and he's not that fast, and then he's getting faster and faster and faster and faster and faster and faster. Does that make sense? Fart propulsion. It works. Actually, it doesn't work, but let's pretend that you're in space and somehow it works, and you just really, they had space bean burritos that day. Okay? Do you guys agree? This is the graph? So he starts off with, here's the most important part. This is the trick, all right? This graph is a graph of the distance versus time. Corresponding to that graph is this graph of velocity versus time. If I graph this thing, it's going to translate to a graph over here. How is that graph going to look? Over here, did he have a high velocity? No, but he did have a velocity. Yeah, what's up?
Well, wouldn't the velocity be, I'm not in this class, but I'm going to be anyway. So, wouldn't the velocity be below zero because when he's not moving, and then, let's see.
What do you think? You guys agree with her? When he's not moving, the velocity is below zero.
Or it's at zero.
When he's not moving, it's at zero. I agree with that. When he's not moving, it's below zero. I don't agree. That means he's going backwards.
Yeah. That's...
All right. So when he's not moving, the velocity is at zero. That makes perfect sense. He's not moving right here. Now let's talk about 1 second later. Is he moving?
Yeah.
Yes. So there is a velocity. Is it a high velocity? No. So it's something like that. Okay. Let's talk about 2 seconds. Is he moving? Yes. Is it a velocity? Yes, there is a velocity. Is it a high velocity? Okay, it's probably not. Is it higher than this point, though? What do you guys think? Come on. Is it up here or down here? You think it's here? What do you think? We're talking about the velocity. Is he moving faster or slower than at 2 seconds compared to 1 second? Moving faster, so it can't be down. It has to be up. Right? Let's keep going. Over here, is he moving faster or slower? Faster, right? Something like this. You want to know what this graph looks like? So, if I were to draw a velocity time graph and I had a straight line like that, the corresponding distance time graph would look like a curvy line like this. In fact, it would be what we call a... Say it out loud. Say it with confidence.
Parabola.
A parabola. So you see how the parabola actually relates to the straight line? Both of these are graphing the exact same scenario. I'll even do one up from that. I'm going to do one more. What would the acceleration time graph look like? The acceleration time graph is he accelerating at the beginning? Is his velocity getting faster? Yes. Is he accelerating around the middle?
Yes.
Is his velocity getting faster over here? Yes. So it's over here, is that dot supposed to be higher or lower?
Higher.
Nope, it's the same. Because the amount of speeding up that he's doing is the slope of this line. Right? the slope at this point right here is the same as the slope at this point right here. Does that make sense to you? Am I blowing your mind? Come on, help me out here. What's your thoughts? All right. Is he accelerating over here? Yes. These three graphs describe the exact same scenario. It describes the scenario of Jordan standing on his skateboard and doing a consistent fart, and he's just going slow, slow, faster, 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 until he catches up. This graph looks exactly what that would look like if I took my motion detector and I dropped something from here. That would be the exact same. It would give this exact same graph. Yes, question.
So the acceleration graph is just a straight horizontal line because the slope of the velocity graph stays the same.
Yes, because the slope of this thing stays the same. Remember when we were doing that running, walking kind of deal, that slope changed? Then that acceleration graph would have changed. But since it's a constant velocity change that's happening, then this acceleration goes straight. All of these three graphs describe the same thing. Here, let me make this relevant to you guys in terms of physics. I'm telling you that the scenario that we described was skateboard, fart, go, right? Starts off slow, ends up going faster. That's the exact same scenario as if you were to jump off a cliff. It goes slow, it gets faster and faster and faster and faster and faster, right? If I were to put my my motion detector thing up here and drop the pen from here, and you guys go, ah! It would graph the exact same thing. Okay? And then when he lands, all right. I'm all about the fart jokes today. Why is he accelerating if you jump off a cliff? Go.
Because the pull of gravity is getting
Because
stronger
gravity is pulling them down. All right? Does gravity pull faster later on? Really? There's a gravity machine. As I jump out the window, the gravity kind of goes up, and we all just go, oh! And then when you land, the gravity, turns off? And we all just start floating? No, the gravity's the same. It's always pulling down. It's constantly pulling down. It's pulling me down right now. The only reason why I'm not falling is because there's the floor pushing me up, right? But when I drop something, gravity's pulling down. And it doesn't pull faster when it's over here than when it's over here. It's the same amount of pull, right? Constant acceleration. That acceleration is constantly pulling you down. Does that make sense to you? We good? This is calculus. I kid you not. If you take this graph, and I'm going to put it in calculus terms that you won't understand for another 3 years, that's fine. If you take this graph and you take the derivative of this, it will give you this graph. If you take the derivative of this, it will give you this graph. And would you like to know how to take the derivative of something? Or at least I'm not going to show you exactly how to take the derivative of something, but you like to know the concept behind taking the derivative of something? It's that trick I showed you about finding a slope between those 2 points and then taking that bead and sliding it down. That's what taking a derivative is. Now there's a lot of math that's involved behind that. I'm just explaining the concepts of it. But I want you as Algebra 1 students to be able to translate from this graph to this graph to this graph. Just kind of like getting a feel for it. You don't need the exact equation. You don't need that line to match up perfectly. I'm fine without that. But I want you guys to kind of get a feel for it. I promise you I'd let you out by 10:15. I lied. Sorry. All right. I'm done with class. I'll see you guys later. Question from